Oscillators, a basic training by me, Nick Amey. In this training, we will cover what is an oscillator, some different types of resonators, quartz crystals in particular, specifying an oscillator, and a little bit of how to talk about oscillator noise. So let's begin with what an oscillator is. An oscillator is an electronic circuit which is providing an output waveform that fluctuates between two states in a repetitive and periodic stable manner. An oscillator needs two parameters to function, a positive feedback mechanism and a gain greater than 1. This is known as the Berghausen criterion, and the loop gain must be greater than 1 and the feedback loop must have a total phase shift of 0. So in the diagram on the right here we see an amplifier. We see the output of the amplifier is fed back to the input, and on the feedback loop is a frequency controlling element. So that's something that acts as a bandpass filter. If we look at what happens when we start this circuit, you see a graph there showing frequency versus gain, and we see white noise because when you first start an amplifier there is some white noise inherent in the circuit. And an amplifier does its job and it makes that bigger, and so we have a signal coming out of the output of the amplifier, and as that signal goes around the feedback loop it reaches the input of the amplifier, and so it begins to have some gain, and quickly the frequency controlling element will filter out all of the noise except for whatever frequency it resonates at, and so we see a little peak begin to appear. That peak is input to the amplifier, and so on the output of the amplifier has done its job and made that peak greater. And so after a couple of milliseconds, this amplifier has built up to give a stable, clean output of a single frequency, and that frequency is determined by the parameters of the frequency controlling element. And so we have an oscillator. Quartz crystal oscillators are normally used in electronics at the moment because they give a very stable output and they're very well understood. So quartz crystals has a very high Q, so they give a very clean frequency output, and since it's been the dominant frequency controlling element in these types of circuits for around 30, 40, 50 years now, it's very well established in the manufacturing, so it's very easy to do large manufacturing in the low costs as is needed in the electronics industry today. However, quartz is not the only resonator type. There's quite a few different options out on the industry at the moment, so let's run through them and have a look at the different parameters that they cover. If you just want a very basic oscillator, you need something that switches on and off at a reasonably regular state, but you're not overly interested in the accuracy of the timing of that. You could start with a very basic LC circuit. A lot of us came across these at school. We used a 555 timer and we put a capacitor and a resistor network on the output of that, and what happens there is the capacitor is charged up and then it discharges through a resistor, and in discharging through the resistor controls the discharge time, and so we have a time constant developed over that. This type of circuit is not very accurate. It's just stable to maybe 10% if you're lucky. It'll change frequency depending on the humidity, the temperature, the air pressure. Pretty much any parameter change will cause a frequency change on these things. They're very, very cheap obviously, so we're talking fractions of a cent here. And it's hard to get above about 500 kilohertz in these circuits. So there's definitely scope to do better than that, but there are times when that's the right option for you. If you want to go up in the frequency control chain a little bit, you might move to a ceramic resonator. Ceramic resonators are products that will give you a stability that's a little bit better than an LC circuit, but not much better. So again, best used in a situation where you will need to execute some code, so you need some clock signal, but it doesn't really matter to you if that clock is changing a little bit. Perhaps there's no communication with the outside world, it's running in isolation, you just need it to run sequentially, keep the bus speed running. So these things might cost in the region of a few cents. and you can now run in the megahertz region, so maybe 3 megs to 70 megs, that kind of area. They are in fact a piezoelectric material called lead zirconium tantalate, PZT. So there is a coupling between its shape and its resonant frequency. However, if you want something where time is actually starting to become important to you, the timing of events and synchronizing events between one area and another, then you're going to be looking at a commodity quartz oscillator. So commodity quartz oscillators are the types of things that we might store in large volumes and sell in reels of thousands. Stability for these products for a TCXO can be less than a ppm, or for a standard crystal might be in the range of 100 ppm. The frequency ranges for these are 1 megahertz up to 800 megahertz, and there is of course the 32.768 kilohertz devices which are used for watch crystals and real-time clock circuits. So the resonating principle that's happening here is the piezoelectric effect of quartz crystals. That means that we shape the quartz to have a physical shape with a resonant frequency, and the coupling between electrical and mechanical principles as described in the piezoelectric effect means that there is an electrical resonant frequency. So as we change the shape of the crystal, so we change the resonant frequency both electrically and mechanically. That's not the only form of resonator. These days there's also a new resonator on the market known as a MEMS oscillator. MEMS oscillators have stabilities and frequency ranges which are very comparable to commodity quartz oscillators, and that would be because when they first came into the market they were looking to be a parallel product to the quartz oscillators, so that was their target, to hit the similar spec. The actual fundamental principle that's going on inside is it's a piece of silicon that's been shaped and formed to have a resonant frequency. So there is in fact a piezoelectric coupling between silicon here. It's very, very small, so it's produced in the fabrication process, very similar to normal CMOS fabrication. Maybe one of the main differences between a MEMS oscillator and a quartz oscillator is that the MEMS resonator system will have one frequency that it resonates at, and then there'll be a PLL circuit that's shifting that into different frequencies, whereas with quartz you tend to grind and lap and polish the quartz to make a specific frequency from that. So the main reason why the two might differ, it would be on the phase noise. On a phase noise plot for a MEMS you might see a bit of a hump caused by the PLL circuit, although I have to say they've got very good over the last few years, so they're not such a problem as such anymore in the applications they're used for. However, there are times when that's just not good enough, and there we would move up to the next level, which would be a high stability quartz oscillator. So that could be an OCXO, and an OCXO in today's world is available down to frequencies in the range of 0.2 parts per billion or 200 parts per trillion, and that would be the type of frequency deviation you might see caused by temperature from these products. Costs are going to be a lot higher. Frequencies are going to be more limited because it's much more complicated to design these, so I can't do all the plethora of different frequencies needed, but I can give very stable stuff in sort of 10 megs, 100 megs, 80 megs, very fixed frequencies like that. Internally what's happening is it's the same as a commodity quartz crystal. It's a piezoelectric coupling of the resonant shape of the quartz, but we will go into a little bit more detail on the next few slides about how we achieve the better spec from these parts. If you want better than that, the next step up would be a rubidium oscillator. Here what's happening is a rubidium physics package is coupled to an OCXO, and the combination of the two will correct the aging that's happening in the OCXO. So the stability is similar to what you get in an OCXO, and then where the improvement is in the very long term. So over the year you'll get a lot less frequency drift. The cost is a lot higher. The internal frequency of these things is 6.834 gigahertz, but then your external frequency that the customer is receiving is normally the OCXO frequency of 10 megahertz or something like that. The actual resonating principle that's happening for rubidium is that we are going to excite the rubidium-87 gas. We are going to excite it with a microwave frequency, and that's going to create a hyperfine transition as the shells of the electron shift from one state to another. They give off photons as they do that, and if we get the microwave frequency exactly at that 6.83 gigs, then it gives off the maximum number of photons, and so by looking for the maximum number of photons, we know that we've got the right microwave frequency, and that's our feedback loop. That's our resonating principle for these ones. If you want better than that, you're going to shift into a cesium clock. Cesium clocks have even better aging performance than rubidiums, so now we're looking at figures like 1 × 10 to the minus 12. These things are going to cost between $50,000 and $100,000, so much more expensive. The concept that's going on inside is similar to the rubidium in as much as you've got a microwave transition, but instead of rubidium gas, it's now cesium-133 atoms, and they are going to go through their own hyperfine transition, but instead we're going to need 9.192 gigahertz, because that's the microwave energy frequency necessary to create the hyperfine transition. One thing that's worth noting with a cesium clock is that the current SI unit of time is the second, and it is defined by the decay of a cesium atom. So a cesium clock is the definition of a second, which raises an interesting question to say, how could you possibly be better than what is the definition of a second? But there are products that are better, and the next in the range would be a hydrogen maser. A hydrogen maser is a product with an aging even more improved on the cesium clock. So here it will be 3 to the minus 16 in 24 hours, something in that area. Although the cost is going to be a lot higher, so $250,000 to $500,000 for one of these. Internally, it's a similar concept to a cesium and a rubidium in as much as the hydrogen atoms are doing a hyperfine transition. Because it's hydrogen, it's a different frequency again, so we need 1.42 gigahertz for this one. But again, the output frequency would be 10 megahertz as derived from a quartz crystal, and the physics package is just correcting the aging of the quartz crystal. And finally, for this slide, the optical clocks. Optical clocks are clocks where the internal frequency is running at tetrahertz, so that's up close to the visible light frequencies, hence the name optical clocks. The aging on these things is equivalent to sort of 1 second in 15 billion years. I want to say that they are in development only. I'm giving this talk at the end of 2024, and beginning of this year I was seeing things being discussed about how they could condense it down from a science experiment to being something that could be sold. And then at the end of this year, I saw 2 or 3 companies that were offering these things as 5U rack mounted objects. So products that could be sold, although they were telling me they could only produce 2 or 3 of them in a year. So I would say watch this space. These products are coming into the market quite quickly at the moment. Okay, I have a line across there in the middle of that slide. That's because the products above that line are PCB mountable devices. So they're things that you would buy as a electronic component, solder them onto your PCB and build a clock out of it. Whereas the units below the line are standalone units. That means they are rack mountable items that you would buy, plug into your rack, connect via a cable to something else, and they would give you a frequency output on a BNC connector or something like that. Okay, so there's a summary of the different resonator types that are available in the market today. So these next slides, we're going to talk about how quartz crystals function, so how quartz oscillators are working. We're going to focus on that because quartz is the dominant resonator principle used for most oscillators in the market at the moment. So on the top right there we have the symbol for a quartz crystal. You can see it's a square with 2 lines either side and 2 electrical connections coming off. That represents a lump of rock with 2 electrodes plated on either side. And what we're going to do is we're going to cut through a lump of quartz crystal rock, and we're going to cut at an angle of 35 degrees 15 minutes. That angle corresponds to what we call an AT cut, and the curve down at the bottom there shows the temperature behavior of an AT cut crystal. What you see is it's rotationally symmetrical about 25 degrees with a rollover point at -20 and +60 degrees. And so that's what it is. That's how the product behaves over temperature. And then we come to the next slide, where we're going to show a simple package crystal oscillator. Here what we're going to do is we're going to incorporate that rock into a basic circuit to make a resonator. So looking at the circuit there, what you can see is the amplifier, represented as a buffer in the middle, a second amplifier which is isolating what's happening on the feedback circuit from what happens on the outside world, and then we see a couple of capacitors. And the capacitors are used because we're running the crystal in the inductive region of its behavior, and so the capacitors are pulling the crystal over to the point where the inductance and capacitance cancel each other out, and we're only left with the resistive losses in the circuit. A simple package crystal oscillator might be accurate to 10 to 100 ppm, might draw about 50 milliwatts, and as I said, the temperature response would look very similar to the curve down there. We can change the temperature response a little bit by changing the cut that we use for the crystal, but it's going to follow that y equals x cubed behavior that we see on the graph there. If we want to move up the technology tree from that, we've got a voltage controlled crystal oscillator. A voltage controlled crystal oscillator, we swap those capacitors for a thing known as a varactor diode. A varactor diode is a diode running in reverse bias, and so when we put the bias across it, the P and N junctions move apart, and the harder the bias, the further they move apart, and so the larger the capacitance that they represent. What we do is we have a third pin to control that, and if we put a DC voltage onto that third pin, we can change the capacitance value of the component while it's live running in the circuit. That gives us the ability to tune the circuit up and down, and we might be able to pull the circuit perhaps 100, 150 parts per million while it's running. So that gives us some way to correct the frequency or to tune the frequency, which you might do if you've got a comms system wanting to speak between 2 different oscillators, and you want to get the 2 clock frequencies to be identical. So you might choose to tune one frequency up or down until it's perfectly aligned with the other one. The accuracy of these things over temperature is the same. There's no correction, so it's the same curve as we saw before, and the power draw is somewhat similar to what it was before. However, we can do an improvement, because the next level up here is what we call a TCXO, or a temperature compensated crystal oscillator. And in this circuit, we're going to use the voltage controls that we had before, but the DC voltage is going to be connected to a circuit which has a temperature response. And we're going to try and make a network of components to build a temperature response which is the opposite of the temperature response of the crystal. So if we look at the graph down there, we see the blue line, which is the AT cut crystal response, so that's the frequency over temperature response of the crystal. And we see an orange line, which is what we're trying to achieve with the temperature compensation network. So if we can get the temperature compensation network that pulls the frequency down when the frequency is trying to move up by the crystal, then we can cancel each other out, and we hope that the overall network here, the full system, will have a temperature response very similar to the green line. So that would be trying to hit a zero line through the middle where one response is cancelling out the other. If we want better than that, we can shift to a completely different technology. So here we're looking at an OCXO, that's an oven controlled crystal oscillator. So if we're trying to remove the behavior over temperature, an alternative method is simply to heat it up and hold it at a very stable temperature. and that's how these products behave. So we've gone back to a simple package crystal oscillator circuit in the center, and then we put the whole thing inside a heater and we heat it up and hold it at a stable temperature. As long as the ambient temperature doesn't go above or close to the control temperature, then we can hold the temperature very, very stable indeed. And in fact, in an OCXO, it would normally be around plus or minus 0.1 of a degree change, while the ambient temperature is changing from perhaps minus 20 to 70 degrees or something like that. The other thing we're going to do here for a high-end TCXO is we're going to shift to a different cut. So we talked about it being 35 degrees 15 minutes for the AT cut, and we had that blue line on the graph. But for an OCXO, we're going to use what's called an SC cut, which is a stress compensated cut. This is actually a double rotated cut. So we're going to hold the original block of quartz at one angle, so that is 34 degrees. And then we're also going to rotate it through a second 22 degrees, and that double rotation, which is very difficult to control in manufacturing, so it does affect the price of these things, but that will give us that temperature response that we see on the graph below. Why do we want that temperature response? Well, what we've got in that temperature response is we have a flat spot that's somewhere about the 90-degree mark, and that flat spot means that when we do have that 0.1 of a degree temperature shift over while the external temperature is changing, the frequency shift that we're going to see caused by that is going to be very, very low, and we can achieve 1 ppb or even less than 1 ppb with these products. So it's a massive improvement on a TCXO or the products below. The downside, of course, is that if you heat something up, it takes a lot of energy to keep things hot, and so this is now going to draw something like a watt or 5 watts or something like that. And the last of the quartz crystal oscillator types, and to move into the next level of technology that we saw in our resonator slide, is a rubidium oscillator. And I said before that a rubidium oscillator really is about correcting for the aging response of an OCXO. So we've got the frequency stability of an OCXO, but over time that is going to change frequency. It's going to age just a tiny bit, and we can remove that by using a rubidium physics package. So let's have a little look at what's going on here. The diagram shows an OCXO, same as before, and we have this new element called the rubidium physics package. Inside here is a rubidium gas held in a cell, and we're going to excite it with microwave energy. That microwave energy has got to be that very long, precise frequency of 6.83 gigahertz. When that microwave energy hits the rubidium-87, the electrons in the rubidium-87 gas start moving from one space to another, and as they do that hyperfine transition, they give off a photon. Then we have a light detection system in here that looks for the number of photons that are being detected and gives us a signal, and then we can say that if we have the maximum number of photons on that cell, then we must be getting into the area of being very close to that frequency. If that frequency is developed from the 10 megahertz coming out from the OCXO, and we have a multiplier that brings it up to 6.83 gigs, and so as the OCXO begins to drift over a few weeks, we might see less photons received on the cell there. With less photons received, we know something's wrong, so we have a system here that then pushes the frequency of the OCXO to build it back up again to correct for that, and so we begin to have a feedback loop that's pushing the frequency of the OCXO as determined by the rubidium gas here. One of the things to note about this is that the rubidium physics package on the long term, so averaged over really long time periods like a year, it's incredibly stable. We've done it, we put one on the lab and left it there for a year, and I think we got 4.7 parts per trillion or something over the year. But in the short term, less than a second time periods, actually it's not very stable. It's quite noisy. And so there is why we have the OCXO, because the really high Q value of the crystal oscillator here is being used in the short term, and then it's being steered by the rubidium physics package in the long term. Okay, so that covers the different types of quartz oscillators and I hope gives an insight into how they work. So in this slide, I want to cover the basics of how to specify an oscillator. Let's assume you want to buy an oscillator and you approach a company like ours and you ask, I want an oscillator. What are the basic questions we're going to need to do between us? The first one, of course, is you ask for something that gives a frequency, so we better establish what frequency you want. And a low-cost commodity oscillator is available in a really wide range of frequencies because we're simply going to grind and lap the crystal and that will give us a frequency that you require. A high-performance oscillator, when you start looking at OCXOs or even TCXOs, the technology behind getting a really stable frequency becomes a lot more complicated, so the range of frequencies that I can offer you is a lot more limited. But nonetheless, we need to establish what frequency you want. Supply voltage might be the next thing that we need to talk about. Oscillators run on electricity, so we need to know what supply voltage you're running at. Normally that might be 3.3 volts or 1.8 volts or something like that. The supply voltage to an oscillator is going to need to be very, very stable. Any noise on the power rail is going to translate directly into frequency modulation on the output. So I'm hoping that you've got a very stable power supply. And then when you come to ovenized oscillators like OCXOs, they're running a lot of power. It might be something that you want to consider. Maybe you have a 12-volt line on your power supply that you weren't using, and maybe that's going to be an isolated power supply for an OCXO and give us the extra current that we need. Talking of power, yep, warm-up time and steady-state power. If you're using an OCXO, then it's going to draw a lot of power for the moment that it's warming up, and then there'll be a different definition for the power once it's in steady-state operation, as we call it. So the example on the right there shows a product which has a need for 800 milliamps at 3.3 volts for 5 minutes while it's warming up, and then after 5 minutes that will have dropped down to 350 milliamps. That'll be a decay curve, it's not a stepped transition there. I have had a situation once where a customer had a power supply and it didn't quite have enough to give the full range at the moment that it warmed up, and that meant that at the moment it warmed up the rubidium was struggling because different parts of the system were not seeing the same power, and so it never really hit a stable state in its operation because one part had started before another part because it didn't have the right power for it. So there's some lessons to be learned from that. The next conversation we have could be about the output type. It's an oscillator, it's going to make an output switch on and off, but do you need that output to be a really nice clean square wave like a sine wave? Seems obvious, doesn't it? Except that square waves contain a lot of rising edges which can be very noisy in high frequency areas, so you might want a sine wave. Sine wave would be the purest frequency wave that we can give you. Or maybe you're using a really high frequency and you're looking for a differential pair, something like an LVPECL or an LVDS output, because that's going to help cancel out the noise in the high frequency and give you better transmission lines over your PCB. Then we come to frequency tolerance. Frequency tolerance is a phrase we use to mean the measure of how accurate the frequency is when you first put the device onto the PCB. So we would normally measure that at 25 degrees. As you saw on the curve on the earlier slide, that's because that's the rollover point for an AT cut crystal. So we're going to discuss how accurately, how close are we going to hit that original frequency that you asked for when you first put the product onto the PCB. And that might be something like 0.05 parts per billion at 25 degrees or something like that. This tolerance can be removed using a pulling function. So if you're using a VCXO, as we showed in the other circuit, you can put it on the PCB and then you can adjust a calibration pin, if you like, and you can pull that frequency up or down to bring it into spec. The next parameter we might discuss is called frequency stability, and here we're talking about the change of frequency as caused by temperature. So now we're looking at that curve that we saw for the AT cut crystal and how that's going to behave. As I said, I can change that curve a little bit by changing the angle that we cut the quartz at, and I'm going to try and hit your requirements, but I'm also going to try and hit your budget. So how tightly do we need to control that? And we might say something like 0.3 ppb typical over 0 to 70 or something like that. So we're going to have a temperature range and a frequency stability in the combination there. Which brings us to the next one, temperature. And yep, we're going to need the range to be defined. You need to be careful with these products. A lot of other electronics products are available in very standard frequencies. So you might have -40 to 85 as a commercial temperature range. And that's fair enough if that's what you really need. But bearing in mind for quartz crystals, there's a direct relationship between the physics of how it works and how it happens over temperature. So if you really don't need -40, if you're working in something like a server cabinet and you're never going to see temperatures below -10 or even +10 degrees, and you're never going to see temperatures above 70 or 80 degrees, then that's a much reduced temperature range for us to control behavior over, and that's going to make the product easier for us to design. So that is going to have an effect on the cost for the product. Then we have pulling. So we talked before on the VCXO about having that input where we can change the frequency as we're running the device. And if we are going to use that function, we're going to need to define it, and we might define it on an OCXO as something like ±2 parts per billion as a minimum amount that you can pull the frequency, and we'll give you a control voltage. We might have an input pin and we say, look, the midpoint could be 2.5 volts, and then you can pull it to +2 ppm if you go up to 5 volts, and to -2 ppm from what it was if you pull it down to 0 volts or something like that. I did have a colleague that discussed the idea of an oscillator that didn't have enough pulling to overcome its own aging, which I can see being a problem. So if a product has got an aging specification and you're going to run it for 10 years, you better have enough pulling over that 10 years to be able to remove all the aging that it's going to have. I would say that 99% of the products I've ever seen would be able to achieve that, but I have heard a story about a product that didn't offer that, which was a bit of a surprise. And then finally for this slide, we're going to talk about digital control. So an oscillator is just going to run, make you a nice stable frequency, but you might want some control mechanism over that. And at the very basic level, that could be a digital control pin that when it's high, the oscillator is running, and when it's low, the oscillator stops, something like that. In that case, I would still ask the question, when you say stopped, did you mean that you wanted the output buffer to disable, but the internal oscillators to keep running, meaning there's no output available, but when you need that output, you can switch it back on very, very quickly because internally I'm still running. But therefore the current draw, when you switch it off, is going to be about the same because I'm still doing the same amount of work internally. Or alternatively, would you have a function where you can switch off the internal oscillator? That would massively reduce the current draw from milliamps down to microamps. But when you switch it back on, you might need a few milliseconds before you have a stable oscillation again. So something to think about there. Other oscillators like OCXOs have functions like lock pins to tell you when the internal lock has been established. They have pins that tell you as an output to say my temperature is now stable and things like that. So other forms of digital control. In this slide, I want to talk about some of the more advanced features of an oscillator specification. So in the last slide we talked about the basics that we would need to establish between us, and now we're going to go into some of the more complex areas of how an oscillator works and how we define it. So let's look at aging. We've talked already about the fact that quartz crystals might change frequency over time, and we call that aging. What's happening there normally is there's a stress relaxation on the blank and some outgassing happening, and that causes a logarithmic decay of the frequency. So predominantly you're going to see more aging in the first few months or year of running the device, and then it will dissipate down to nothing. But nonetheless, you might need to define that, and it's normally on the specification, and it might be defined in how many ppb per year, or on a high-end product it might be in how many ppb per day, per month and per year. On from that, we have load coefficient. So this is a measure of the effect of the load of the output on the frequency of the oscillator. So a standard oscillator circuit is trying to drive some input buffers. So the output from us is driving some inputs from you. We call that a load, and it could be represented as a capacitance, and we might say as standard we test things with a 15 picofarad capacitance hanging on the output in order to simulate the load of running your inputs. And if that isn't 15 picofarads, if it's a little bit higher, a little bit lower, then what's the effect on the frequency? Because it's going to have an influence, and there we might describe something like a 5% change in load, and it might cause so many ppm, 5 ppb or something, as a maximum change in frequency that you could expect. So that gives you an indication of what's happening on your PCB and why you might see a frequency different to the frequency that we told you it was going to be. Might be because there's a different load in your PCB to what we had in our test circuit as we designed it. The next one would be pushing. Pushing is an interesting term we use to describe how much the frequency changes when the supply voltage changes. So you could say it's a modulation of the frequency caused by the supply voltage change. One of the most common problems here would be noise on the supply voltage line. So if you've got some digital switching on the same line and you haven't got enough filtering, then that digital switching will translate into a frequency modulation that you're seeing on the output. And here again we might describe it as something like a 5% change in the supply voltage will cause so many parts per million in the frequency shift. Then we have shock, vibration, acceleration, and all the other environmental stresses that components have to survive. And we might well put on the data sheet something like mechanical shock as per IEC 68068 test 2227. We might define the level of shocks and the amplitude of the duration, and we will lay all of that out on the data sheet, and you might have some specific application where there's a specifically high shock that we need to meet or something like that. I've seen guys in the rail industry have got some very interesting shock clauses caused by the vibration of very high masses on the rail. So we can do tests to prove that products can meet those specifications. It's worth thinking about, when you look at that on a data sheet, almost always that is survivability being defined. So we're saying that the product before and after those environmental stresses will still be within specification on the output. It's a different thing to say what will the frequency do during that shock and that vibration. So just be careful what you ask for and how you define it on the data sheet. Retrace is another one of the more advanced questions we might have. So retrace is a measure of how much the frequency changes when I switch the oscillator off and switch it back on again. Sounds a strange thing, but on an OCXO where the frequencies are parts per billion, it could be that it's just not quite the same, or it takes many, many hours until it's back to where it was. And so we would have a definition of retrace that might say something like, I'm going to run the oscillator 24 hours on, switch it off for 1 hour, switch it back on for 1 hour, and then tell you how much the frequency is close to what it was in the beginning. And it might be something like 0.2 part per billion or something. So we're talking very small amounts. On a standard SPXO, these things are not worth worrying about, but on something like an OCXO, it becomes significant. Same goes with gravitational force, this change of frequency caused by change of gravitational force. Might sound a bit strange, why would the gravitational force change? But we have what we call a 2G tip over test. So that would be where the gravitational force of the Earth is 1G, and if I turn the device upside down, then it experiences negative 1G in the same plane. So one minus the other makes for a 2G, and we call that a 2G tip over test. And therefore we can measure the frequency of an oscillator in one direction, turn it up the other way, measure the frequency again, and ask whether it's changed, and we can repeat that through 3 different axes. And define which axis gives us the maximum change and therefore talk about how much change it is. The changes we're talking about here are tiny. We're talking 2 to the minus 12 per G, something like that. So again, it's only relevant on really high-end OCXOs, rubidiums and those kinds of products. And the same would be said for magnetic field sensitivity. So changes in magnetic field sensitivity, especially on products where microwave cavities are used and things like that, are significant, they're measurable, and magnetic field changes due to large chunks of metal moving around, we can detect when lorries are driving past the lab in our site and things like that. And the frequency change you might observe caused by this could be, when measured, in the range of plus or minus 2 to the minus 11 per gauss. So again, very, very small stuff, but relevant if you're looking at stuff that's accurate, like a rubidium or an OCXO. So final point on this slide, those parts marked with a dot are things that cannot be removed, whereas those not marked will be corrected for. So you can use the pulling and you can remove the aging, you can remove the effect of the load variations because they're normally stable on your PCB. The retrace is known once the power's back up, but the other things are, you're going to have to live with them. So the other things that I've marked up there are things that you should be aware of. They're going to happen during its operation, and if the sum total of all of that puts it outside of what you can use, that's going to be a problem for you. Okay. In this final slide, I just want to cover the very basics of oscillator noise. So the function of an oscillator is to give a very stable frequency output, and obviously we can measure the instabilities of the frequency output and we can call that noise. There are many different ways to measure noise, and we're going to do some separate slides talking about each one of those. So I'm not going to go into great detail here, but the most common methodology for measuring noise and defining noise could be phase noise. That's a frequency domain measurement where we're measuring the power in the frequency domain of different frequencies as offset from the carrier. So you might get a spec that reads something like at 1 Hertz the power will be at least 108 dB or less than the carrier frequency, and so it goes out as we move further away, there's less power in the spectral range. Spurious is another way that we measure frequency noise. Spurious would be caused by something, some digital switching, if there were such a thing inside the oscillator, giving other spikes of noise that you can see, and you might define those spikes as in the terms of their power in reference to the power of the carrier frequency. So we might have a spec that says something like spurious frequencies will be less than 80 dBs, and that means that there will be at least 80 dBs difference between the power in the main frequency that you're looking at and the power in any spurious. Jitter is another way to define noise. Jitter is a time domain measurement, so now we're using things like oscilloscopes to measure jitter, and we're looking at eye diagrams, and we're looking at fast Fourier transfers of the shape of that, and we might have different things that we can define. So we might say that the period jitter after 1,000 cycles is going to be less than 1.5 picoseconds as a root mean squared or something like that. That's another way to define the noise. And the last one I wanted to cover in this slide is Allen deviation. Allen deviation is a complex way to look at the short-term stability of an oscillator. It's a mathematical function used from large amounts of time domain measurements where we measure the noise of every repeating cycle, and we look at whether it's we look at it statistically, and it gives us a figure that we can use to compare one clock to another and say, is this one as good as another one, even though there might be different frequencies. So Allen deviation is a log-log method, and so we'll come up with figures that say something like at 1 second it might have an Allen deviation of 5.5 to the minus 11, at 10 seconds it might have 7.1 to the minus 12, and so on. There are many ways to measure noise for an oscillator, but that's just a summary of them. So thanks very much. That was a brief summary of general state of oscillators across the industry, and hope for some insights into how they're manufactured and what to look out for them. There's some further reading here if you're interested, and we'll be doing a lot more of these in the future, so do check back for more.